Today I'm talk about Steins algorithm, or it's also known as the binary GCD algorithm. So you probably already know an algorithm to compute the greatest common divisor, namely the Euclidean algorithm. And today I'll show you another algorithm to compute the greatest common divisor. I also recommend you having a look at a video by Richard Borchertz, which is also about this topic. It's quite interesting, so I'll link it and you can have a look at that too. So let's see how we can let's see a different way to compute the greatest common divisor. So let's say we have two non-negative integers, a and b, and now let's assume that without loss of generality, a is at least b. Okay, and now let's see. So at first, if b is 0, then the greatest common divisor of a and b is a, so then we are done. And otherwise, we have that we can divide by powers of 2, so we write, let's say, a as 2 to the, well, let's say, nu a times something, let's say, ma, and b as 2 to the nu b times mb. Okay, and now we compute the GCD of 2 to the nu a and 2 to the nu b and save it. And now we set a to be ma and b to be mb. Okay, and the next step is, so if necessary, change probably there's a better word for it, but interchange a and b, that's the word, right? So if necessary, interchange a and b so that we have again that a is at least b. Okay, now comes the main trick. The trick is that now our a and b are coprime to 2. Now we can calculate a minus b, and as a and b are odd, this is even. And so we can again write this as, say, well, let's write it as 2 to the, well, let's call it ua minus b times ma minus b. And now we set a to be, well, at first we check that if a minus b is 0, then we just return b. Otherwise, we set a to be our previous a minus b, or well, let's make it easier. We set a as m a minus b. Okay, so that's our new a, and again, if necessary, interchange a and b again, such that a is at least b, and then we go to step 3 again. And there's a little mistake, so let me tell you. So don't return b, but return b times this GCD of 2 to the new a, 2 to the new b, which we have saved before. Okay, so let's see at first why this calculates the greatest common divisor. So, well, for the case b equal to 0, it's clear. And so let's see what happens. So if we so let's make some small remarks. So the GCD of a minus b and b is the same as the greatest common divisor of a and b. One can easily see that because, well, so if we have, let's say, p divides a minus b and p divides b, then it also divides a minus b plus b, so it divides a. And we can also go the other way back, so if it's p divides a and p divides b, then it also divides a minus b. So that's why the greatest common divisor doesn't change if we look at here at a minus b and b. And these powers of 2 are not of any concern for us, because we already know that a and b are coprime to 2. So that means that we can just divide by these powers of 2 without changing the greatest common divisor. So at any point in this algorithm, the greatest common divisor of a and b doesn't change. So a and b change, but not the greatest common divisor, so that's invariant. And we certainly know that in the end, if b is 0, then we get the greatest, if a minus b is 0, that the greatest common divisor is just b of these numbers which are coprime to 2. And of course we have to think about this thing here, because we have divided by powers of 2, so we have to remember that. Okay, so that's the algorithm. Then also it's quite clear that it terminates, because in any step we make the number a smaller, because we subtract by b, and then we also divide at least by 2, because a minus b is even. So yeah, certainly a gets smaller in any step. So if b is less than a, then a afterwards is at most b. So wait, that's not exactly true, but afterwards a might either be, so this a minus b divided by 2, or it might be b. Okay, so that's about this algorithm. It's actually also quite performant, so one can use this instead of the Euclidean algorithm. And now I just wanna mention some fun generalizations. So I don't know, probably these are not used in practice, but one can think about it. But before I mention the generalizations, one more thing. So if we, one thing why this algorithm is quite fast is because dividing by powers of 2 on a computer is just a shift operation. So we just shift numbers, and that's easy for a computer to do. Okay, so now let's take another setting. Let's look at a polynomial ring. So let's say we look at k of x, where k is a field. And now we wanna adapt this algorithm to this setting. So let's say we have f and g in this polynomial ring. And now the thing we can do is we write f as, say, sum from 0 to n ai x to the I, and g as sum from j equal 0 to m bj x to the j. And now what we do is so multiplying by a element of the field k doesn't change the greatest common divisor. So we look at f divided by a naught and g divided by b naught. So that certainly doesn't change the greatest common divisor. And now we can, so we set this as our new f's and g's, and then we get f divided by a naught minus g divided by b naught is equal to sum I equal 0 to n, and then we have ai divided by a naught x to the I minus sum j 0 to m bj divided by b naught, and then x to the j. And for the 0 term, so we can write this as, so the important thing to note is that the 0 coefficient of this polynomial is 1, and of this it's also 1. So we get that x divides f over a naught minus g over b naught. And so what we can do, we see again the greatest common divisor. So let's say degree f is at least the degree of g. And now what we can do is that greatest common divisor of f And G is the same as greatest common divisor of f and also of f divided by a naught minus G divided by b naught, and then, oh, there shouldn't be a G naught, just a G, and G. So, and now we see what we want to do. So the algorithm, I just sketch it. So in the beginning, divide f and g by x as often as possible, so such that both are coprime to x, and then we subtract the polynomials, and then again we divide by x. So then we divide f over a naught minus g over b naught by x. And so obviously this leaves the greatest common divisor unchanged if we assume that so if we have our polynomials which are coprime to x, we assume that as we have already divided by x as often as possible. And so this leaves the greatest common divisor unchanged. And now the thing is, so if we divide by x, then certainly the degree of this thing here, if we divide it by x, this gets smaller, and so after some finite steps, this algorithm will terminate. So that's good, so we can use this algorithm also. Actually, it's also a shift, so dividing by x is a shift of the coefficient. So one could imagine that maybe it might be actually fast. Maybe if one implements it in a good way, it might be fast. I tried it in Sage Math. That certainly wasn't fast in comparison to the Euclidean algorithm for polynomials. So yeah, you can try it. I would be interested if you can implement this in a fast way. Okay, so that's it for polynomials. Then let me mention two more things. So actually there's also a algorithm for the greatest common divisor in the Gaussian integers, which is an analog of the binary GCD algorithm. You can find it. You can find a reference to the paper on the Wikipedia. So I don't know what the name of the paper is, but if you look at the references in Wikipedia, you can find it. And then another rather silly generalization. So probably that's also quite slow, but I haven't measured the time yet, how fast it is. So namely, you don't need, so here we looked at powers of 2. So one could wonder, well, do I need a 2 here? And you don't need a 2 here, so you can take, let's say, any prime p. Maybe you can even do it more general, but for primes it certainly works. So you take a prime p, and now the thing is, now you can think about doing something similar as for polynomials. So for polynomials, we divide it by the constant coefficient. So what could one do here? So if we say, let's say, we fix p prime, and now we divide as often as possible by all, let's say, k, which are at most p. So instead of dividing by 2, we divide by all numbers between 2 and p as often as possible. So that's in the beginning. And we save these. We calculate the GCD by any means we have. Is p, if p is small, that's no big problem. So we calculate it. And now we are at first in trouble, because if we want to subtract these numbers, normally it shouldn't be divisible by p. So how can we go on? Well, we need to find inverses modulo p. So if we have an inverse modulo p, then we can use the idea from here. So we multiply with the inverse modulo p. So let me maybe write it down. So if we have a, and then we set a to a times a inverse times b modulo p. So this is a number which is at most p minus 1. And so now and now we can, if we look at a minus b, then this is certainly congruent to 0 modulo p. So now we have to be a little bit more careful, because this we multiply by something which changes our absolute value. So it's we have to be a little bit careful. But on the other hand, it's not that bad, because afterwards we can divide a minus b by at least p. Probably, maybe we can also divide it by some higher powers of p, or also by some other values k which are less than p. And so actually, if we modify this algorithm, it not just leaves the greatest common divisor unchanged, but it's also quite clear that the algorithm terminates. So the numbers get smaller, because otherwise we would have a problem. So that's about a slight generalization, which probably isn't really fast. And also to calculate this inverse modulo p. So this here is an inverse modulo p. We might need, for instance, the extended Euclidean algorithm. So yeah, we still need something to compute these inverses, and maybe we actually need the Euclidean algorithm, but still we just need it for numbers smaller than p. So we could also just pre-compute these A inverse values for all numbers smaller than p, and then we wouldn't need to use the Euclidean algorithm during the run of this algorithm. So I know, especially this last part here was quite sketchy, so I hope you could at least get the idea. So yeah, if you want, you can try it out, or if you have questions, you can also ask me. And yeah, I would also be interested if you have run any experiments on the runtime of these algorithms, and if you can maybe get better results with runtime than I did. Okay, so that's it about this algorithm. So I hope you had a little fun. If you want to know more about it, I guess I could also give a link in the description so you can look at that. And you can also look at the video I mentioned in the beginning. I'll also put a link. So that's it for today. And have a good day. Bye.